Welcome back, Eigen family. So, we have another episode today that is, I hope, of interest to you guys. So, we're going to be talking about Mr. Wolfram and his physics pathway to theoretical physics. Of course, guys, first, make sure you like, share, comment, and subscribe if you haven't already. And then check out the websites, eigenbros.com, Eigenbros on Twitter, Eigenbros on Instagram, and Eigenbros2 on TikTok. And thank you, patrons, once again. We greatly appreciate your support. And if you guys would like to become a Patreon yourselves, check out patreon.com/Eigenbros and support your boys. $1, and you get a 30-minute podcast every week.
Yeah, at least a 30-minute podcast.
Yeah. We usually go over it sometimes. So.
Yeah.
Around random bullshit, though. So if you're only
true.
here for the physics, then maybe you could save your $1.
Yeah, save your $1. The Patreon is more to get to know us.
Yeah.
Become an intimate member of the Eigen family. And sounds warm, like a blanket.
Yes.
Nothing. No. Very PG.
Yes.
Yeah.
Just hand-holding.
Yeah. But anyway, let's get to the start of the show. Today we were talking. There's a lot to discuss, right? Wolfram's toe.
Yes, Wolfram's toe.
His theory of everything.
Yeah, so I guess basically, I wanted to give a little summary of what it actually entailed, right, from at the beginning here. So Wolfram basically, you guys probably know that he came out with this theory of everything last year during, the beginning of quarantine. I think it was the beginning of quarantine, wasn't it? Maybe middle-ish beginning. I forget exactly.
Yeah.
But he came out with it around the same time as Eric Weinstein, and there was this whole kind of, goofs of everyone's theories of everything. I think Sabina Hassenfelder even made a song about all these theories of everything. But Wolfram, he came out with a theory of everything that had to relate to his research of computational physics. So it's a little bit different in the sense of maybe traditional theories of everything that you may know of, with these kind of analytical methods of solving or finding an equation, like some kind of Lagrangian or something. And to contrast it with Eric's, he's got equations as well. But Wolfram's is more of like a computational, very visual, pretty different version of theory of everything. And he also calls it a pathway towards a fundamental theory. So he's not even claiming that it's a theory of everything, but he has an idea that it could prove or demonstrate a lot of the physical laws that we know of for our universe. So I guess with that being said, we have a video that I wanted to show first of just Wolfram himself kind of giving a nice, really quick explanation of his theory in general.
Yeah.
So he's got, if you go to Wolfram's website, his Wolfram Physics Project website, he's got a nice little image called the visual summary, is what he calls it. And it shows the important aspects of his theory. And we're going to go over that and kind of touch base on that, because I think that's the most important. That's kind of what you need to really understand the theory in its most broken down form. Of course, it's really vague if you don't read, but hopefully we can do the legwork here and actually make it understandable for you guys.
Yeah, and just to give you some background, Wolfram himself is a computer scientist, mathematician.
Yeah, I forget exactly his background, but he knew Feynman. He worked with Feynman.
Yeah.
So he definitely has physics background. He was into physics apparently when he was really young. So he's kind of like one of these really like polymath kind of dudes who really his whole life has been spent doing mathematics, physics, computation, that kind of thing. So he's a true straight up just like STEM nerd.
Yeah, he is. Yeah, I mean he went to Caltech, one of the more prestigious schools for his PhD, and actually maybe the top school in physics, right?
Yeah, I think so.
Especially for
maybe
theory.
even today still, right?
Yeah, even today probably. Yeah, and and yeah, so that kind of gives you some of the background, but he mostly focuses on developing a computer science kind of background to his software called Mathematica.
Yeah.
And the whole database thing, and yeah.
Yeah, Wolfram is responsible, if you don't already know, for Wolfram Alpha and Mathematica. Those are his two big claims of fame.
Mm-hmm.
You know, they're huge feats in computational mathematics and programming, I guess you could say.
Yeah. Because I wanted to give some context, because people, I'm sure some people don't.
Yeah, for sure.
Don't know who he is, because like even in our field, when I mentioned who the hell is Wolfram, professors would be like, it's just some guy. And I'm like, wait, what? I mean, he's making pretty important contributions. Yeah. Like, I can plug in an integral and he can solve it. That's kind of cool.
Right.
But anyway, yeah, so he has a lot of background in this computational thing, and this will give you more context to his approach, right, to
not even physics. Really. This first video will just kind of give you a summary of the important elements.
All right.
To start off.
So
it's maybe like 2 minutes or so, or maybe less.
All right. This was good?
Yeah, can you blow it up?
Yeah, let's do it. Buffering. Wow, in 2021, can you imagine?
Needless to say, in an effort to get to sort of a fundamental theory of physics, things are pretty abstract. But with it turns out one can get some level of visual and other representation of what's going on. So let me give you the kind of the high level sketch of the high level sketch, and then we'll start going into more detail. So the basic question, an idea is, can there be sort of a simple underlying rule that can generate all the physics that we know? So let me just give you a little tour of this. So this is kind of roughly, this is sort of a representation of one of the kinds of rules that we're interested in. It's a rule that basically rewrites pieces of a hypergraph, and the rule gets applied many times. When you apply the rule many times, you generate this large hypergraph that sort of in its continuum limit can behave like space, like something that's a manifold, has a manifold-like structure. So this is kind of this is sort of where space comes from. Then what one's interested in doing is looking at the sort of the relationships between the different updating events that are happening here, and that produces this kind of causal graph over here, and that's sort of a representation of space-time. And as I'll try and describe, one of the really cool things that happens is that with certain assumptions and things that I'll describe, special relativity turns out to be something that you can then derive as a property of these systems. And more than that, you can derive first the vacuum Einstein equations, and then the full Einstein equations with energy momentum tensor and so on from this, which I think is pretty amazing and cool. So it turns out that this kind of picture of there's this big hypergraph that's getting rewritten in all these ways, that's one of the things that happens is there's ambiguity in those possible rewritings. And so while here I just showed a particular hypergraph coming out, the truer picture is that there's a whole kind of graph, whole first tree, but eventually graph of different forms of this hypergraph that can come out with different kinds of rewritings that can occur. And it turns out that those kinds of different rewritings that happen make quantum mechanics not just something that you sort of put in, but something that's kind of inevitable in this setup. And what turns out to happen, so this picture.
Okay, so Wolfram kind of gave a nice little breakdown of the important aspects of his pathway towards fundamental physics. So he's got those, and actually, can you pull up go to the visual summary just so we can see it.
Mm-hmm.
Not the video, the website. So I have a link.
Oh, gotcha.
Called Visual Summary. So there, of course, you guys can go to I don't have it on there, really.
Yeah.
Okay, well you could go to the larger notes.
Gotcha.
So I've got the other notes section on there. It should have the Visual Summary. Under where?
Underwear?
Note links at the top.
Here it is.
Yeah, there you go. So really the visual summary is kind of the important thing that you need to look at when you're looking at Wolfram's theory here. So we'll be talking about, I guess, maybe like 7 of the different hypergraphs. So The hypergraphs are these really weird branch-like structures that you see in his little visual summary. And we'll put it on the podcast as well if you guys want to see it visually.
Yeah, and if you're a listener, just Google Wolfram visual summary.
Yeah, but we'll also try to describe it to you for the audio listeners only. So he's got several sections. I think he's got maybe 7 or 8 graphs on here, and really I'll just talk about 7 because one of them is kind of related to quantum mechanics, and I didn't want to get into that. But he's got the hypergraph structures. So basically, if you think about how this thing starts, is Wolfram has these nodes, right? So he starts with nodes, and they're just based on, and then he has a connection between them. And then what you can do is with these nodes and these connections, and he also calls these connections links or edges, you can actually create a rule where you can change the connections. So let's say if you had some connection, you can add on connections, let's say with a rule. And then he does this and iterates it over many, many cycles, and that eventually produces some kind of spatial structure. And in the visual summary, that spatial structure is in the bottom left corner, the blue mass that he has that has a bunch of wires connected to nodes. And Wolfram calls that space in his theory.
Would you dare call it a fiber? I'm just kidding.
A fiber bundle?
I'm kidding.
No,
I'm kidding. But it does look like a connected network of like a spider web, like fibers and stuff.
Yeah, it looks like a spider web or like one of those like EEG scans of like brain neurons or something.
Right, yeah. That's like a mapping essentially. Yeah.
Yeah, so that is what creates those nodes and links being iterated over many generations are what creates that structure. And Wolfram also mentions that there's many ways to create those structures. So you can create different you can create different structures based on different rules that you may apply in different orders. So it's not necessarily the same structure will be created every time, but that's an example of one structure. And then looking on further into his theory, he's also able to build what he calls as the causal graph from that structure itself. So what that means is the causal graph has to do with the different paths that each of the iterated nodes and links can take. So let's imagine this: if you have let's say you have a node with one link connected, so that look like a line with 2 dots connected to it, and he iterates and adds another line and dot to one of those connections. You could think about maybe you could add a line and a dot to 2 different sides of that node and link connection. So there's many different ways that you can create these iterations, which will eventually lead to a causal graph. So there's a branching effect. So you can have an A structure and a B structure that branches off from that main initial state that you started with.
Right.
And that creates a causal graph. So he uses that causal graph to actually show time. So as that hypergraph evolves, he claims that to be time, which is indicated with the causal graph and the different branches that it takes. Does that make sense?
Yeah, I mean, his little rules, yes.
Yes.
I mean, like, he uses the word computational universe a lot, so it's kind of like he wants it to make. I felt like he wanted it to be known that this is more of like a way to see the universe, right? Yeah.
Right. Like, so it's like it's a model for how the universe. It's basically what it comes across to me is it's a model of the properties of it's a model trying to represent some of the important properties of physics of our universe. Yeah. But let's move on to the next video one. Sure. So this is a more in-depth video that he has. So I chose this one specifically because it's basically like the first video, only he goes into more depth into this one. I think this one's maybe like 5 or 6
minutes. Tons and tons of material on it, but there's kind of a visual summary on here, which is kind of the rough picture of sort of how we think the universe is built. So one question is sort of what's the universe fundamentally made of? And so sort of a fundamental question there is what is space? Well, that's not a question people usually ask. Ever since Euclid, it's just been, well, space is this thing that things exist in. You can take a point, you can put the point anywhere you want. The point has no extent. It's infinitely small, and you don't have to say where it is. But actually, we don't think that's right. We think that actually space is not a continuous thing where you can just put the point wherever you want. Space is discrete. It's actually made of a bunch of discrete points. Now, in a sense, we've seen this story before. When we think about something like water, we might say, well, water is a continuous fluid. We might say, well, we can pick any point in the water and there's still water there. But it's not true, because actually water is made of a bunch of discrete molecules, and you either hit the water molecule or you don't. It's a discrete kind of thing. Well, we think space is like that too, that space is not continuous, which is what has been assumed in both physics, mathematical physics, and sort of it's a Euclid and after kind of assumption that space is somehow continuous. We don't think that's correct. We think instead that we should think of space as being made of kind of atoms of space, just as materials are made of atoms of materials. And those atoms of space are just points, disembodied points. How is space sort of put together? Well, we think that space is a big network. And really all that's said is there's a point, and the point has certain neighbors in this network. The point is connected to other points. We might just say space is abstractly made of a bunch of elements, and these elements have relations that relate them to other elements. And that's what space is, in a sense, that it's just this giant network. It's actually formally a hypergraph. So an ordinary graph is something where every point, pairs of points are connected together. In a hypergraph, you can have more than 2 points connected by a hyperedge. But the basic idea is it's this giant hypergraph that contains many points. Like in our universe, there might be 10 to the 400 points, a very large number of points in our universe. And then just like water on a large scale seems continuous to us, so space on a large scale seems continuous to us. The microscopic atoms of space might be 10 to the minus 100 meters across. By comparison, like a proton is 10 to the minus 15 meters across. And so very, very tiny on that scale. But the idea is that space consists of this discrete hypergraph. And then the question is, okay, so if that's the case, there's sort of what happens is on a large scale limit, space seems continuous and three-dimensional. On a small scale, it might not be that way at all. And it also is not to be guaranteed that space is three-dimensional as opposed to 3.1 dimensional, as opposed to something else. All of those things are determined. There's no sense in which these points exist at coordinates in space. They just have a relationship to each other, and it's an emergent thing that there's a large-scale continuous structure to space. That's kind of the notion of what space is. By the way, I should say that there's a question of well, what exists in the universe? Normally in current sort of physics, we've thought of there's sort of a background of space, and then there's matter and energy and things that exists in space. In this model, it's very minimal. The only thing that exists in the universe is basically space. There's just this giant hypergraph, might have 10 to the 400 nodes in it, and everything that exists in the universe is a feature of this hypergraph. Now, that might seem bizarre, but it doesn't seem quite as bizarre when you start looking at something like...
Okay, so let's touch on some of those things real quick. We're going to continue on. I just wanted to pause there because he goes back to another image that's kind of unrelated.
Yeah.
But he mentioned discreteness. So Wolfram makes a big claim that space is discretized in his theory. So basically with these nodal structures... So that would be the points in his theory that connect the links or connect to the links. Mm. He's saying that basically those are like the quanta of space, or like the atoms of space as he calls it. So he's saying that space can be discretized. So then, of course, my initial reaction was like, oh, I don't know about that, Wolfram.
Yeah, same.
People have tried discrete space-time already. And that wasn't didn't go so well, right? They had some things, people tried discreteness when there was problems with quantum field theory, right? But then instead of discreteness, they came up with renormalization, which allowed you to get rid of those infinities without having to do discrete space. And one of the problems that I saw online, at least, I didn't confirm this, I didn't know of a good way to prove it, but apparently Lorentz invariance gets screwed up with discrete space. Mm-hmm. So then I was like, okay, how is Wolfram going to make this claim? So I researched more, and I found out that, okay, actually, Wolfram did mention here that he said that the atoms of space in his theory could lie in the region or on the size scales of like 10 to the minus 100 meters. And then, of course, a lot of the physics people in our audience will know of, the Planck length, which is 10 to the minus 34, I think, or 33 meters, something around there. And that basically says that anything we really know about physics, we can't really talk about beyond that size limit. So Wolfram kind of...
those energy thresholds,
Right. So Wolfram kind of skirts around discrete space problems by making the nodal units small enough to where they lie in the region where we can't really talk about physics in the same ways anymore.
Right.
So I'm like, all right, that's fine. You can do that. So we can get away with discrete space-time or space. I keep saying space only because Wolfram handles time a little bit differently in his theory. So yeah, his structure is space. And then Wolfram also mentions, what was it? The size, which I think I mentioned already.
Yeah, the size. Well, I kind of want to comment on that because it's a little bit. I'm concerned with why he just didn't go with like the fundamental right now as we know it. Like that's theoretically that's the smallest fundamental like unit discrete energy, right? The Planck, the Planck lengths or whatever.
No, it's not really. I mean, it's like let's make this distinction that it's not like that there's a hard limit.
Right.
The Planck length is simply just it was formulated in a way to make it so that there's a quantity of length that was independent of whatever your system of measurement was.
Right.
Like a Planck length will be the same if you're an alien or if you're a human because it's only based on fundamental constants like g, h bar, and c, the speed of light.
Right.
So it's not that it's the smallest unit. It's like the smallest length we can talk about with any reasonable it's the only reasonable unit we can talk about within our understanding of physics. So there's nothing saying that something can't be below or smaller than the Planck length. It's just that we don't really have a language to be able to discuss anything beyond that length.
Right. Maybe I'm just asking here, shot in the dark.
Okay.
So because like that's something that kind of perturbed me about this, like just wondering why he just didn't go with that, because like you're saying, if the Planck length is this it's sort of calculated using all these constants, you should get the same ratio, right? Because these constants in the universe are supposed to be universal, right? In some sense. Yeah. So you should get the same relation in theory across all space and time.
Yeah,
right?
In theory, as long as we're assuming that all space is,
uniform,
right? And it's the same everywhere, right?
Yeah.
And I think Wolfram actually claims that maybe it's not. I don't know why he claims that. I forget exactly why.
I could see looking at his little map thing, it looks all kind of weird in all these other spaces.
Right.
Yeah.
That was another problem with it. I didn't get enough time to think about it, because we did this podcast kind of short notice, but I didn't get to think enough. I was always wondering, like, how does this... Because one of the questions I had was, how do the different structures of, let's say, these spatial these hyperstructures, how do they correspond? Like, how does this physical picture change with different types of spatial hyperstructures? Like, does that have anything to do with the curvature of space? And I think he actually talks about this in some of his other lessons, but I didn't get enough time to actually, like, really dive deep into that, so I can't comment.
We'll probably talk about this more. These are open questions that were sort of concerning to me, because he's going to a regime that, for all intents and purposes, seems like we will never be able to. Like
Won't say never. But.
Well, I know, but it's like even the energy of like a Planck, like the fundamental unit is so small. Like
well, Planck's not an energy.
No,
but,
it's like
you mean just the order of magnitude?
Just the order of magnitude
of
the Planck constant. Yeah.
Because that's in the minus 34 region, right?
Yeah.
So
it's very small.
Yeah.
And yeah, so I don't know. I was just like, man, he's making
He's
this
kind of
really
sweeping his
untestable.
physics under the rug.
Yeah. He's kind of making this really untestable. But anyway.
But to be fair, Wolfram does make some claims. He says that some of his stuff, he has some things that are testable with his theory. Mm-hmm. Although I did not actually check that, so we'll have to just take his word for now.
Yeah, for now.
Until further. But hold on, Juan. I want you to skip ahead a little bit because he goes into a structure regard. No. So careful. I want you to go back. Yeah, look after that switch. I want you to go right after that switch. No, after that. So keep going a little bit. Yeah, there you go. Okay.
In a sense, when we work out how much of the activity of the universe is involved with the maintenance of the structure of space versus being involved with all the things we care about, all the electrons and protons and all those kinds of things, it seems like it's maybe about 1 part in 10 to the 120 is the stuff we care about. And the other, all the other parts in the 10 to the 120 are all just to do with the maintenance of the structure of space. Okay, so how does that's sort of the structure of space? How does space, what happens in space? What is the progression of time? So in our way of thinking about things, time is a process of computation. What's happening as time progresses is that this hypergraph is being progressively rewritten. There are rules that say, for example, if you see a piece of hypergraph that looks like this, rewrite it to one that looks like that. And all the time, all over the universe, this is what's happening. There's this structure, this hypergraph that represents space, and that structure is being continuously rewritten. And that progressive rewriting is the progress of time. And that kind of this particular model of sort of the irreducible progress of time, this phenomenon of computational irreducibility that I mentioned before, is something that is fundamental to the progression of time. That also explains how thermodynamics works and a bunch of other things. That there's this kind of notion of computational progress is the progress of time. Well, so the first thing you might say is, okay, that's great, but how can that possibly be right? We've known since 1905 this idea of special relativity that kind of say that space and time are sort of the same kind of thing. How can you be saying that space is the extent of this spatial hypergraph and time is this progression of computation with time? Well, it's a little bit subtle, but here's how it works. So what happens is when you are an observer embedded within this universe, so you're part of this hypergraph, there's a question of what can you actually tell about what's going on in the universe. And it turns out the only thing you can tell is about updating events and the relationship between updating events. In a sense, what you can see is every time one of these rules gets applied, it's like a little event that happens. It's a little thing that happens to this network. And you can ask the question, when you look at those different events that happen, what is their causal relationship? That is, an event may be not able to happen yet because the input that it needs has to come from the output to some other event. And so there's that defines kind of this partial ordering of events that defines kind of this thread of causality, this kind of set of causal relationships. And from that, you build this kind of causal graph that represents the causal relationships between events. And it's, in a sense, a very extreme version of this. Imagine you're an observer in this universe. And imagine that in the universe, only one event is ever happening at a time. But where that event happens kind of runs around all over the universe. You might say that theory can't possibly be right. After all, I can see that things are happening elsewhere in the universe. But the point is, you don't get to see anything until that event has come to you, so to speak. So as that thing zips around, you're kind of frozen until you get updated, and you can't tell what's been updated until you're updated. And anyway, in the end, what you've realized is the only thing you can actually sense is this kind of causal network of the causal relationships between events. Well, it turns out there's another important phenomenon that we call causal invariance, which has the feature that you might say, well, I'm saying, I think I forgot to say one thing, which is when you do these updates, there may be many possible updates that you could do in this network. And the question is, which one do you do first? Which one do you do later? Well, it turns out that when there is this phenomenon of causal invariance, it simply doesn't matter in what order you do those updates. It doesn't matter to the causal graph that you get out. the graph of causal relationships is unaffected by the particular order in which you did those updates. It's something that is just dependent on the structure of the system. It's something that has this causal invariance property. Well, that causal invariance property and the fact that one's just dealing with this causal graph turns out to be the story that leads to special relativity. It turns out that the phenomenon of the idea that sort of physics is the same whether you're stationary or going at 1/3 the speed of light turns out to be just that those are just different ways to sample this causal graph, and you're sort of guaranteed to have the same causal graph because of causal invariance. And actually, you can go even further than that, and you can discover that when you look at the spatial hypergraph, you can start asking questions like, let me go into a little bit more detail here. You can start asking questions about the spatial hypergraph. Let's start looking at a few more details about how this works. So there's.
Okay, so Wolfram said a lot there, but mainly the thing he was talking about, the causal graph and causal invariance. So I guess I could go ahead and explain a little bit on that. So to briefly summarize once again, Wolfram was basically showing the causal graph, which is basically the graph that that can be created after you've created the spatial hypergraph. So the spatial hypergraph, again, starts with some initial nodal structure connected with links that you go ahead and set initially. Then what happens is you get these pathways and branchings as you add a rule onto that first structure, and you iterate it over a certain number of iterations. Wolfram claims our universe might be like 10 to the 400 iterations of nodal or hypergraph iterations, whatever you want to call it. And then with that, you can create the causal graph. The causal graph basically shows those pathways that you can lead to those different structures. Mm-hmm. It's the pathway of those certain iterations. So that's what he treats as, I guess, like the time evolution of his system.
Yeah.
So then once you do that, he says that there's a particular property that shows up in certain hypergraphs. Not all hypergraphs have this property, but certain hypergraphs have this property of causal invariance. So then, of course, you're asking, what the hell is causal invariance, and why would I care? So the thing is, Wolfram has this property he discovered from his theory called causal invariance, where let's imagine you have an initial nodal structure or initial hypergraph, right, that you set. When you make an iteration, let's say that it branches into a hypergraph A and a hypergraph B. So you start with a hypergraph 0, that branches into an hypergraph A and a hypergraph B. What his causal invariance theory says is that any branching will eventually result into a convergence of the same structure. Mm-hmm. So your graph A and your graph B, if it is causally invariant, will then have one of its possible iterations on the third iterations or the second iteration cycle. So that second iteration cycle will have a possible convergence with A and B. So let me say that again in a more understandable way. So structure 0 is what you start with. A and B is the first iteration of that structure with the rule set. A and B then also evolve on a second iteration into multiple different graphs. Yeah. So let's say A can evolve into 3 possible new graphs, and B can also evolve into 3 possible new graphs. Causal invariance tells you that one of those 3 new possible evolutions with A and B will converge with one another, at least one.
Gotcha.
So with that property, apparently, Wolfram says that you can then say that if you looked at just the pathways of A, and if you just look at the evolution paths of B separately, they both have the same exact graphical structure. So that is what he means by causal invariance. What that really means, I don't really know, but apparently he uses that to invoke the laws of special relativity. So just knowing that, you can say that for something to be causal invariant, Wolfram can apply his certain regime of relativity as looking at, and what he does is he says this because these causally invariant structures of graph A and graph B, let's say, can be broken up into what he calls foliations. So foliations are just slices of each of these times.
Yeah.
So you've got those two iterations, right? You can slice those up into these time-like regions. And of course, when I'm saying time-like, you can already pretty much guess as a physicist that's talking about like relativity, right? Because we think of things like space-like and time-like when we're analyzing like Minkowski diagrams, for example. So Wolfram tries to do the same thing with his little hypergraph structures.
Branching,
these causally invariant hypergraph structures. He's able to make a kind of relativistic regime, he claims, using that. I'm not going to go into the detail because I don't even understand it really. So that's all I can really tell you, just a kind of big picture of it. But yeah, so his causal invariant property is important for that relativistic regime in his model. I was then trying to ask myself, I was like, what is an example of a non-causally invariant structure? Apparently, he's saying that most of his structures that are built from these hypergraph rule sets are not causally invariant. So it's like a very small percentage. I think he said like 5% of the graphs that he looks at are like causally invariant. So Wolfram is claiming that for our universe to be one of these hypergraphs, it has to be one of these structures that is in fact causally invariant. So, and I guess to get back, an example of one would be like a structure that had a bunch of loops. So if a structure has a loop onto itself, so let's say if you're thinking of your hypergraph structure, I should probably explain the hypergraph structure a little bit, but
Sure.
Just to explain again, so like a hypergraph you can make as like a collection of 2 points or whatever, how many points you want. It's like a matrix. You can think of it even like a vector. So like if I have a vector x, y, I can think of those as two different nodes, node x and node y. So with that, if you have a hypergraph that has a loop, let's say an XX, that means it's an X that loops onto itself. So the connection loops onto itself. So that would be an example automatically of like a not causally invariant system, because if you're looping, you're going backwards in time apparently if you break it up into exfoliation or to foliations. Maybe a little bit hard to see. This is kind of a visual project, so I'm trying to explain as best as I can there, but just to long story short, loops in your hypergraph structure or in your causal graph structure will fuck up your causal invariance. That's one way. But then there's other ways to do it as well. If things don't converge properly, then it's not. But certain properties of the system can have causal invariance where a branching branches and then will recombine after every iteration.
Yeah, so my question, it lies in more of the physical interpretation of it.
Yes,
because the causal invariance rule, the sort of principle that he's following, in physics, or at least in Einstein's theory of relativity, his rule really is the natural constraint is the speed of light, right? And in this one, there's more of an abstraction and not really a physical constraint, right?
Yeah. Well, this is kind of the thing about Wolfram's theory. He's kind of it looks like he's really obsessed with all of the real like deep fundamental properties and like axioms and things that we've discovered from these certain regimes in physics, like general relativity, quantum mechanics, even classical mechanics. And it's kind of hard to even see what the physical picture is. Like it's almost, so Wolfram's theory, to really sum it up, it's like it basically is an abstraction. So he starts with this abstraction and then he layers or overlays the physics on top of this abstraction.
Right.
So his physical arguments are almost null. Like I don't see any real attachment to physics. Like I can barely hold on to what he's saying because it's basically an abstraction that's just overlaid onto this, or I'm sorry, the physics is overlaid onto this abstraction. So he's overlaying these properties. So, you've got a relativity like Lorentz invariance. You've got like these time-like, space-like structures and things like this.
Right.
He's overlaying those properties that we've discovered through physics onto this abstraction, and then building this structure that tries to follow or have these kind of properties. He's trying to look for objects in his theory or in his abstraction that will follow these properties.
You're saying they corroborate?
Yeah, he's got an idea of what the property he wants. And then he tries to invoke that onto his theory. Of course, this isn't really the greatest in my opinion, it's not really the greatest way to do science, in my opinion, because it's like you can have all these nice theories and like really beautiful mathematics that you can make work and make fit to your idea, but it doesn't mean it's right. It's kind of like the conspiracy theory mindset. You know, the conspirator people have a conclusion in their mind and then invoke evidence to support the conclusion. Mm-hmm. But to me, a scientist is someone who kind of sifts through evidence first and then doesn't have any idea what a conclusion is going to be and builds a conclusion at the end. Wolfram's theory feels more like the former, the conspiratorial mindset, where you have a conclusion already in mind and you're invoking your evidence, or you're supporting your theory with evidence after, or you're supporting your conclusion specifically with the evidence.
Yeah, and I think this is a feature of it, though. I mean, I don't think so. Your claim is that his theory is not really scientific.
In my opinion, it's not the way I go about doing science. I think it's a dangerous way to do it.
But you're saying by a strict definition, it doesn't classify as a scientific theory, because a scientific theory would have predictability, right, in some way?
No, I'm not saying it's not predictable. I'm not saying that at all. Because Wolfram even claims that it has some kind of predictability
it does have
as well.
It does have predictability.
Because he has certain aspects of the theory that have these weird intricacies or idiosyncrasies. But I'm not even saying that that's not science. I'm just saying that to me, it seems like it's almost like I could see it being right sometimes, but to me, it seems like a real, like you're living on the edge of doing science if you're trying to do things like that. It's a very risky way to do science, in my opinion, because it's like you have your idea, you have your own subjective interpretation of something, and then you're trying to put reality on top of your own subjective interpretation. Mm-hmm. It's not really, to me, how I ever approach anything scientific, because I feel like I could come up with 20 different theories that I invoke physics onto that could look like the right thing. Yeah. But it's not really like, how do you know?
Yeah. Well,
right? I will fitting your model. Yeah. Or you're fitting physics to the model.
Well, I will say it feels wrong because modern science is built on discovery. You know what I'm saying? You're uncovering something.
Yeah. Yeah.
Hopefully not with any priors. You have a hypothesis. You have an idea of how things might work.
Yeah.
But I think the way he approaches his computational universe approach is more, you run these simulations, you apply these certain set of axioms, set of rules, and once the system corroborates kind of what you see, that it maps onto physics in a way that makes sense. This is kind of how he approaches quantum mechanics, which is also kind of confusing. Because,
I didn't even go in the quantum mechanical regime.
But it's confusing.
It's a little bit tough.
But this is what makes it confusing, because it's like, where is this mapping doesn't seem so natural, doesn't seem so one-to-one. But I get what he's trying to do. I think there is some predictive power, right? Because once you create an accurate map, a mapping, the idea is that you can work backwards, right?
Okay, maybe.
Right. So I think he mentioned that in one of his interviews. He's like, the mapping essentially, or whatever, the causal map,
sure,
in some sense, would give you an outline of, like, maybe guide physics where to go.
Okay.
In some sense.
Yeah, I guess that's why he calls it a pathway towards a fundamental theory, right? Because he's trying to build up this computational structure. So, and I guess you could explore the edges of the theory in some sense and see like what predictions should arise from this.
Right.
But it seems to me almost like, how would you know?
I know.
For me, I'm like, I would never like this doesn't feel natural. I feel like you could give this to any guy if you put him in a closed off room.
Yeah.
He could come up with completely different assumptions. It's almost like, how does Wolfram come up with this stuff? It's almost like he's just picking out things that he likes and then assigning whatever he likes to that particular object. Yeah. But I'm like, at the end of the day, I guess really it could just be a really cool computational tool. So if you wanted to, let's say if you wanted to get into Wolfram's theory and whatnot, I wouldn't think of it a waste of time, because at least you would really have a cool conception and understanding of like working with these hypergraph structures. And at the end of the day, you know, that's mathematics, and that could be potentially used for you know, like a space laundry cleaner 300 years in the future, even if it doesn't pan out for your theory of everything. Yeah. So it's like, you never know, right?
Yeah, because I mean, he gives a good example of like how this causal map, or sort of this rule of being able to set or connect structures together.
Yeah.
He gives a mapping of Europe, and he's like, all the capital cities, what's the shortest path between them, and then it gives you a map of like the most efficient route to take.
Okay, yeah, you're saying like one of the properties of one of the computational tools in his whole Wolfram cloud structure allows you to do something like that. Yeah, and like there's a lot of cool computational things it does.
Right, but I think in that analogy, it served the purpose of saying, oh yeah, you have a real overlay of a map, a physical map of something, and then you have the math abstraction, the math layer, the abstract layer, coming over it, so that you can get something useful out of it in some sense. So now the thing is, like, when you map it onto physics, it might not be so, how would you say, clear, because it's still open to interpretation, like you're saying, right? Like, if I looked at a causal map of quantum mechanics, and then I'm like, let's say that there's postulates, the postulates of quantum mechanics, like measurement or something, has a branch or a node or something, and it goes backwards. How would you know what that backwards went back? Like, you know what I mean? Like, there's a branch connecting two axioms or something.
The thing is, when you're talking about the quantum mechanics one, I can't really speak much, because I haven't understood that part of its theory well enough yet.
Right,
that has to do with the branchial graphs.
Right.
And the branchial graphs was something I kind of ignored.
Yeah.
If you want to look at the visual summary, that's the graph at the very bottom.
Yeah.
But I can't comment on that.
Right, but I'm saying, like, in the abstract, if you have two things connecting, the causal map essentially tells you, like, oh, they have something in common. There's something, you know what I mean? They're from a what was the language he was using? They're from a same sort of
same hypergraph.
Yeah, right. Is that what he was saying?
Yeah. So the causal structure has to do with the evolution of the hypergraph.
Right. So if they have,
and he calls the evolution of the hypergraph, all of those evolutions are an event.
Right.
So he says it like, if you're an observer in the hypergraph, let's say if you're an observer in the causal graph, you would actually be living in that hypergraph structure. And then he's saying that people only observe the events in a causal graph. He started talking about something being frozen in time, and I didn't really understand what he was saying. But apparently observers live within that causal graph structure.
Right. Yeah, it's peculiar. I don't know. I could see this being a useful tool in terms of, like, mapping your, like being able to map what you're doing, and then getting the connections, like creating a network of, like, oh, this, how things are causally connected in some way. Or how things are connected.
Yeah, and that seems useful.
Yeah.
That's almost something you can come up with in an elementary fashion.
How so? What do you mean?
Like just knowing that you can make a map of something. Like, that doesn't seem too uniquely done, but maybe I'm thinking is the power of Wolfram's hypergraph thing is that he's come up with some new kind of computational properties.
Yeah.
Like the whole causal invariance, right?
Yeah.
It's kind of a powerful property that you can utilize to maybe figure out things about these weird hypergraph structures. It kind of reminded me of linear algebra. You know how linear algebra we've been working with systems of equations. Like, you can do that since algebra.
Yeah.
But when you come up with linear algebra, you learn how to use system of equations and apply these real abstract properties to them, like finite determinants, span of a vector space, like all this kind of like higher level stuff that you're just like, what the hell does it even mean?
How did this come from? How did we get from system of equations to this shit, right?
Right, exactly. Like, cofactor expansion and shit. And you're just like, what the fuck does any of this mean? But then you're like, okay, it's just like, there are these weird techniques that are invented to show you how to work with large systems of equations.
Yeah.
But you could do that in algebra. It's just that you don't make a connection until maybe you're, a little bit farther along the line,
Right.
like, oh, these are just like these weird properties and techniques that exist within these linear algebra structures, these matrices, and we can apply these weird techniques to them and get like these interesting answers and properties and understand things about our system, that we wouldn't be able to really understand if we didn't have this fleshed out theory of linear algebra.
Exactly. And the linear algebra is the abstract layer, right?
Yeah.
Another abstract layer of how to make the calculations or the computations easier, right?
Yeah.
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 So this
And
might
have
you're
these
saying
weird cool properties.
right. So you're saying that these hyperstructures might serve a similar purpose.
Exactly.
Okay.
So like if Wolfram's physics project fails at the end of the day, the hypergraph I could still see being useful, which is like your time is not wasted. But just maybe his interpretations might be a little bit wasted, but that's okay. We'll see.
Might
Maybe
be a
not.
reach. Might be a reach, but but it seems useful, like you're saying. So you have another video. Is this one worth going to?
I mean, maybe this one I just wanted to put on there. I probably should have started with this, but it's
you
like
think
just
so?
a basic. It's a basic kind of explanation of how the hypergraph, how hypergraphs work. So we
Okay.
can play it.
So if you're still confused about hypergraphs, then
hopefully this will like put the nail in the coffin for you.
okay. So here we go, and we'll play.
What we're going to be talking about are rules which we can represent as rules for hypergraphs, or we'll talk about those in a minute, but we can think about them as rules for graphs or networks. And so for example, we might start off by saying, let's imagine that we have some structure like this, and we have these elements. We're just numbering them 1, 2, 3, 4, and then we have some rule that says how we're going to update this by just looking at the different patterns of elements here. What are we going to do to this structure? And it's sort of an embarrassing thing to admit, but the basic idea for how these rules work is something that is sort of also the foundation for kind of the symbolic programming that is the foundation for Wolfram language, and is actually the foundation for pretty much all of the practical things I've done in computation for the last 40 years. And the embarrassing thing is that I didn't realize that sort of the essence of that symbolic programming idea was exactly what's needed to understand how to build physics out of. And I was working on sort of a slightly different way of setting this up. But the essence of that idea turns out to be the essence of the idea that it looks like we need for physics. So this is just an example of essentially a rule. This is just a sort of more algebraic representation of the thing I was showing earlier, this rule that tells us how to replace one sort of structure in our graph with another structure. Okay, so let's say we start off with some graph that looks like this. Then let's just try applying that rule a few times. This is what we get. So it's the beginning, then we apply the rule,
So I'm going to pause here because he's drawing causal maps. So he has like these little nodes.
No. He's not drawing causal maps.
He's drawing
the
connections between.
He's drawing spatial hypergraphs. So that's the thing you got to remember is there's a distinction between the graphs. There's a spatial hypergraph and then there's a causal graph. There's also like state graphs and multi-state causal graphs and things. He has that on the visual summary. But really the two main ones are the spatial hypergraph and the causal graph. They're different. They're two different graphs.
Gotcha. So
that's the spatial hypergraph.
So this is a spatial hypergraph that you're looking at right now, and it's sort of like these circles that are connected by lines, and I guess the lines tell you.
Right, and the circles you could call nodes, and the lines you could call edges, links, connections, whatever. Yeah,
to give you an idea of what this looks like. And then at the end, you get this web-like structure that maps the space, I guess.
Right. After you've iterated so many rules for these particular initial hypergraphs, you start with these simple structures, and you give it a simple rule, and then you apply that over and over and over again to give you this really complicated geometry kind of, or topology or something. You can even think of it as.
Yeah. So basically, you get like a really sort of intense looking geometric structure. Yeah. So we'll keep going.
Again, and eventually we're getting something like this. So this is kind of the story that I first learned in the 1980s, that even when the rule is very simple, the behavior and the structure that you get can be complicated. So this is an example of what you get after just running maybe 10 steps or something with that particular underlying rule.
Looks like a brain.
So you can say, so what's in the end going to happen is we're going to run this rule maybe 10 to the 400 times, or a rule like this maybe 10 to the 400 times, and that's going to build our universe. Now, I will say at the outset, we don't yet know exactly what the right underlying rule is. It's going to turn out that an awful lot of what shows up in physics, and this is one of the big surprises, is quite generic and actually quite independent of the details of this underlying rule. So we can already derive lots and lots of physics without knowing this final ultimate underlying rule. One of the things we want to find is what that final ultimate underlying rule is. So if we ask ourselves, well, what kinds of things happen with different rules? Here are just a few examples of things that happen with some of the simplest possible rules.
Sheesh.
And what we're anticipating is that when we look at enough of these rules, eventually one of them will turn out to be the rule for our particular physical universe. I'm going to make a little footnote to that. I'll explain later why, in a sense, there can be many different rules that all represent our universe, but we'll get to that in more detail later.
Okay.
Yeah. Does he ever get to it, Terence?
I don't know.
Please tell me.
Wolfram
I need
has
to know.
long-ass videos, so I don't know.
He really does. No, he has a really cool. He has like, what is this? 1, 2, 3, 4, 5, 6 by. What does that look like? 9?
7, 8, 9, 10. 6 by 10, like 60.
60 figures.
Yeah, and it goes on, right?
Yeah.
You can make as many as your heart's content, and then that's also just the one version of that, right?
And these are all look like different tattoos a sorority girl would have.
More like a biologist. Looks like very, like some cells or something, or neurons.
I'm kidding, by the way, but it's these are all very like really cool, abstract looking figures. And maybe you too can have a causal map that you will, or a little mapping, a nodal map.
Okay.
A nodal map of I don't know, of your universe. How about that? Something cute. Like Wolfram, let's work together. We'll create a tattoo company.
But anyway, he has these structures, and you can see that just basically the way that hypergraphs work is, once again, simple structure, simple rules, complex result in a complex shape potentially.
Yeah, so, you're saying because of this invariance, that it gives consequence to other types of invariance, or you said general. You said causal invariance may at first seem like a rather obscure property, but in the context of the models that we have, you're saying that.
Well, this is that quote I took straight from Wolfram's website.
Oh, okay.
Yeah.
So I guess do you want me to read the quote?
Sure. Yeah.
Okay, so the quote says, causal invariance may at first seem like a rather obscure property, but in the context of our models, we will see in what follows that it may in fact be a key to a remarkable range of fundamental features of physics, including relativistic invariance, general covariance, local gauge invariance, as well as the possibility of objective reality in quantum mechanics.
Right, and that was just to touch on, again, the importance of the causal invariance. So it seems like causal invariance is a really key or interesting part of Wolfram's hypergraph structures. So you could get a lot from that one property, apparently. So that's why Wolfram is seeking to look for these spatial hypergraphs that look like something that has the causal invariant property that he mentions in his work. But anyway, that's pretty much it. So I guess I wanted to kind of close it out with, what do you think? What do you think of Wolfram's theory?
I think it's very useful. I think it's a useful metric. It's a useful tool to, like we were saying, finding connections. But I still have problems in understanding how he treats time in this, because he kind of, I don't know. This is this is my interpretation of what he was saying. Maybe it wasn't clear enough. Maybe I didn't understand. Maybe I didn't have enough coffee that day or something. but I got the impression that he treats time decoupled from
So
from
initially.
space.
So this is where the causal graph comes in.
Right.
So you've got the spatial graph, right?
Yeah.
And imagine that's just the one that you start with all the connections and whatnot.
Mm-hmm.
From that spatial graph, you can make the causal graph, because that spatial graph does not necessarily have to look the way it does.
Yeah.
Let's say, just for example, that spatial graph could look 30 other ways, because with that simple rule that you apply over those nodal hypergraph connections, you can do them in different ways. So you can actually get different looking structures that have the same rule set. So the causal graph actually shows you all the different pathways for that.
Right.
And if you have a certain type of rule set, so there's particular rule sets that will actually result in a property called causal invariance. And basically the causal graph is how you actually look at time. So each of those iterations is a moment in time, apparently. Mm-hmm. Beyond that, I really can't say much more, because I'm not sure what all the different branching exactly means. But just know that the causal graph is where time is encapsulated. And then Wolfram claims that you can still get the whole like space-time connection in some sense by looking at the causal graph in his relativity framework. And that has to do with drawing the foliations or the cuts along those graphs and looking at the time-like and space-like dimensions of the hypergraph structure.
Gotcha.
So yeah.
Cool. What about you? What are your thoughts? Closing thoughts?
Yeah, so I guess at the end of the day, I kind of look at Wolfram's theory as an interesting math model. I don't really know how physical it is. To me, I kind of, as a physicist, I need more than just an abstract picture. To be harsh, I kind of feel like this is a little bit of a vanity project for Wolfram. I feel like he kind of, he's a guy who grew up with loving physics, and he's always wanted to do something in physics, as he quite often mentions. And I think maybe he just wanted to, at the later years in his life, do a project and just kind of ham-fist physics in it, whether it's going to work or not. And he kind of wants to deal and understand and work with these cool, interesting properties of physics. And it seems a little bit forced, I'm not going to lie. My personal opinion would be it probably won't pan out in the physical realm. But then what do I know? Who knows? It may be useful.
I think it is.
I just can't see it.
I think it is useful in the sense that I could see it being like he talks about different computational sort of universes or whatever. He's like, in this computational universe, blah, 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 blah.
Yeah.
This sort of mapping or this overlay onto our physical sort of discoveries or understanding of the universe. I think if he builds a good mapping, a one-to-one mapping, I think it'll help guide us towards maybe new physics, maybe like maybe to point where there might be connections where we don't see any.
Yeah, maybe you're right. Maybe there could be something useful that comes from it.
Right.
It's just that so far I don't really see it, just in the fact that there's so much room for interpretation.
Right.
Usually when a theory has too much room for interpretation, you can start just ascribing anything to it, as long as you're just making things fit. So I like things that are more constrained, because you can almost, when things are more constrained, people independently will come up with the same conclusions. Right. If I was analyzing Wolfram's theory just without reading any of his papers, I don't think I could come up with the things he came up with, because it's his own interpretations of things. Like looking at the causal or looking at the spatial hypergraph, I have no idea how that represents space. Like, what about it is space? Where are particles in this system? Like, I don't really see any of that.
Right.
And to me, it just doesn't make sense.
Yeah.
And then also, it's like you're mapping it in 3 dimensions. Like, apparently, the way you map it has nothing to do with the dimensionality. There's another way to find dimensions in Wolfram's theory. So it's like, does mapping it in 2 space versus 3D space, does that change anything about the theory? So there's just so many questions I have that, if I was trying to analyze it physically, I just don't see how I would ever come up with it.
Right.
So to me, that seems like a weak theory. But perhaps, like you're saying, it could just be like a cool kind of mapping of maybe these higher level properties of physics that maybe if you can somehow understand those to a really high level, you can maybe get some cool new things from that.
Yeah, and I think that's why
an abstraction.
Right. I think that's why he's branding it as a path. What did he call it?
A path towards a fundamental theory of physics.
Yeah, because I think he recognizes that it's like more of it's going to be a useful tool, but I don't know. I guess I'm a little bit skeptical, like you're saying, of the utility. It seems like ham-fisting physical principles onto it. Just like, okay, this one maps onto our map.
He's like, my God, physics. I'm like, where? I'm looking real hard. I don't see any.
With the little, what was it called? The
magnifying glass.
Magnifying glass. Thank you. Yeah.
I'm looking real hard for some physics. I'm not seeing shit.
Yeah, and so I mean, look, if you're a representative, if you're somebody who knows the Wolfram's sort of fleshed out model and theory and everything, please let us know. Comment below.
Yeah, sure. Anybody who's got any comments on that, for sure, let us know.
And if you're a representative of his theory and you want to come on the show and talk to us to clarify things,
absolutely,
we'd be more than happy to.
I know he's got his PhD guy, John, I think I forget his last name starts with a G, but John G is always online doing things. Wolfram's constantly doing live streams of them going through workshop.
Yeah.
So, I mean, Wolfram's got no shortage of resources. Unlike Eric Weinstein's theory, where it's just like one paper in a video. So, if you really want to get lost or go deep into a potential theory of everything, Wolfram's is a fun one because there's just so much. He's got so much resources.
Yeah.
But despite it saying all that, he's got a lot of resources, but it doesn't really say that much. So, I'm still trying to figure it out.
Yeah, it's still a work in progress. Don't try to get a. Don't get the impression that it's complete yet.
Yeah, there's no deep fundamental understanding.
No.
But that could be the fun part, right?
That could be.
And you can even figure it out yourself because Wolfram has a nice hands-on walkthrough on Wolfram Cloud, actually, where you can actually mess around with these hypergraph structures. Like, I even put a link in there, one, too, if you wanted to mess with it. I don't think we could do it on the podcast because that requires more equipment than we've got.
But we'll put it on the YouTube video, probably.
But yeah, you can see these nodal structures, these nodal hypergraphs, and you can let them evolve in time, and you can build your own like Wolfram hypergraphs. It's pretty cool.
Cool.
So
all right, folks. Well, if there's any comments or concerns or things you got to say, maybe you got to fact check us or something.
Yeah.
Please comment below.
Absolutely.
Don't forget to like, share, and subscribe if you haven't already. And
then, of course, check out the websites, guys. Eigenbros.com, Eigenbros on Twitter, Eigenbros on Instagram, and Eigenbros2 on TikTok. And then, once again, thank you, patrons. We love you guys so much. Thank you for all your support. And if you guys want to be a patron, you can check us out at patreon.com/Eigenbros. And again, we do a 30-minute podcast on Patreon, extra podcast every week. At least. And $1.
Yeah, $1 will save us all from obscurity. Thank you once again, and we'll see y'all later.
See you guys.
Peace.